Hello, everybody. Welcome back. It's my pleasure to introduce Russell Miller, who will speak to us about countable reductions, Borel equivalence relations, and computable structure theory.
Yes, thank you very much. Trust this is coming through well. So yes, first of all, thanks to all of you folks here for coming. That's not as pro forma as it used to be. Making the trip is a little more fraught than it was. So I'm very glad to see you here and everybody else, and certainly the organizers for putting together this session. I have a title here with 3 different things in it that don't seem to have an awful lot in common to begin with. And so the point here is to explain to you how they connect up and certain ways in which they all affect each other. When I get to the second half of the talk, the computable structure theory part, I'll be telling you about joint work with Turbo Ho and Julia Knight. Can't see the entire list, but Julia is there watching from South Bend. And before that, there's a lot of joint work with a lot of people. King Meng Eng was in on it, and Sam Koski, and Joel Hampkins, and several others. So tell you all about that when we get there. So let's get started with the basic concept, which is a reduction of equivalence relation. Right? I mean, just no modifiers yet. A reduction of one equivalence relation E to another one F is simply a function which takes elements from the field of E and maps them to elements of the field of F in such a way that equivalent things in E always map to equivalent things in F. E equivalent things map to F equivalent things, better way to say it. And non-E equivalent things map to non-F equivalent. Okay. So the idea is that if you had some understanding of F and you had access to this, if you had some understanding of the equivalence relation, big F, and you have some way of working with the function little f, you could put that together to understand the equivalence relation E pretty well too. Now, if you say it just this way, this is trivial. I mean, by the axiom of choice, there is such a reduction, just provided that there are at least as many equivalence classes in F as in E. So of course, we want to talk about the functions. We would like them to be the reductions themselves. We would like them to be computable or at least accessible, definable in some decent way. So the first example, which has been around for quite some time now, is the notion of Borel reducibility. It certainly goes back as far as Friedman and Stanley's paper in the late 1980s, and the notion existed before that, I believe, which there you're normally talking about equivalence relations on a Polish space. For our purposes, let's just say Cantor space today. And the reduction, which is of course a function, is supposed to be a Borel function. Okay. The second example, which actually I think does go back as far as some ideas of Yershoff in the 1960s, is a computable reduction. Different context there. You're talking there about equivalence relations on the natural numbers. And so reduction would be a function from naturals to naturals. And so it's natural to, pardon me, it's obvious to say that the function should be computable, or possibly decomputable for some particular degree, D or whatever else you have in mind. Okay, so these are the basic notions. As I say, a lot of people have looked at this over the years. This is by no means an exhaustive list. I'm just putting up some of the highlights there. So let's first of all just get notation straight. In a way, I feel I should apologize. There are going to be a lot of different types of reducibility here. If you aren't careful, they can numb your brain. So let's just talk about them for a moment. First of all, for relations on omega, I'm going to use a subscript to, the relation is always a function from omega to omega. So the basic question is, what is its Turing degree? And I'll use a D to denote that there is a decomputable reduction. Again, that doesn't mean the reduction has to be exactly degree D, just computable from the degree D. Therefore, when you see a boldface 0 there, that means a computable reduction. Okay. For relations on Cantor space, well, again, the most common notion in the literature is Borel reducibility. So that'll be a B subscript, naturally, if that's common. We will look at some more specific versions as well. I mean, instead of just Borel functions, we might want computable functions from Cantor space to Cantor space, given by a Turing functional, right, that accepts the input as an oracle and computes the output. Or I don't think we'll do this too much today, but you might also say, okay, well, maybe instead of just giving me the input, you give me the jump of the input. And then I have and then still using a Turing functional, I have the potential to compute something more, or several jumps, alpha many jumps. So for reductions in Cantor space, usually we're going to be talking about the number of jumps. Once again, that means 0 equals computable, which is at least pleasing, but okay. We're going to get some superscripts as well. I told you this can mind your num, yes, if you aren't careful, you see. All right, so let me just do an example. Let's dive in on this. Here we're talking about relations on omega, 2 very specific relations where for an index I, you think of I as representing a CE set, WI, just in the standard numbering. And the relation between 2 such numbers, 2 such indices, is that the corresponding CE sets have the same minimum. And just to be clear, if you're talking about the empty set, we'll say that its minimum is positive infinity. And so if Wi and Wj are both empty, that counts as having the same minimum. Second, there's the obvious analog for the maximum. You have to be a little more careful there. For the empty set, the maximum is negative infinity. For an infinite set, it would be positive infinity. And so in this relation, all infinite sets are equivalent to each other, or all I and j in inf are equivalent to each other. The reason for showing you this is to illustrate something. It's a moderately interesting relation in its own right, both of them. It turns out that neither one is computably reducible to the other. Okay. And if you're trying to go in one direction, showing that there's no reduction from max to min, you can actually just do a complexity argument on complexity of the equivalence classes. But there is a direct proof, and it's quite simple, and I want to show it to you to illustrate the first idea that will come up here. Okay, so the idea for a direct proof: somebody gives you an f, a total computable function that they think might be a reduction from the max relation to the min relation, and our job is to enumerate, well, to give an I and a j, which means to enumerate 2 sets on which f messes up. Okay. And of course, we can use the recursion theorem and assume that they know their own indices and wait until f has mapped each of I and j to some other indices. And then the job is to make the maxes the same on the left side if and only if the minima on the right side are different. It doesn't start out that way. So of course, we promptly put an element into Wi. I mean, choosing I basically means defining the program, right? Defining the program for Wi. Now things look good for us if they just stay this way forever. So eventually the opponent over there, W sub f of j or f of I, one or the other, will enumerate some element. And then we want to even things up on the left side. And again, assuming they do respond and don't just give up and lose, they even things up, possibly with n, possibly with a smaller number. But you see that once we get in this situation, you can see the end game right now. I mean, we're going to make things uneven. They're going to even it up. We'll make it even again. They'll have to make their play. And we have lots of space here, and they don't. So eventually, we win. Right? Once they get down to having 0 in both sets, you know, they can't make any more moves, and we win. And the point about this is it only took 2 elements, I and j, to show that f could not be a reduction. Okay, so whatever the F was, there were some two I and J that caused it to mess up. Going the other way, I'm not going to do a proof here actually, but I'm going to point out is that you can't go the other way with just two sets. And in fact, something opposite is true. There are computable total functions G and H, which will take any I and J and output indices which actually do make it look like there's a reduction. Now, G and H are not a reduction because they're not in the right form, of course. I mean, what you're supposed to do for a full reduction is to take any I and output F of I. And for any J, same function should output F of J. We're not quite doing that here, but we are saying that two indices just aren't enough to show that this is impossible. Okay, it's fairly quick to work out what G of ij and H of ij should do. They should just kind of watch what Wi and Wj enumerate and then enumerate things into their own sets accordingly. And in this direction, you can pull that off because the max relation somehow has more space to work with than the min relation. And in fact, there's nothing special about 2 here. You could do the same thing for 3 indices, any finite number you want. Okay. So it is true that there's no full computable reduction from the min relation to the max relation here, but there is this sort of finitary reduction. For any finite number of indices that are given to you, you can pull this off. You just can't do it for all infinitely many at once. Okay. And so the definition that comes out of this, and this is in a paper with Keng-Meng Eng about 10 years ago now, says that an n-ary computable reduction on equivalence relations on omega is exactly what the idea says up there. You can think of this as a single function from omega to the n to omega to the n, or n component functions, either way, single valued. But in any case, you give these functions a single tuple, an n tuple, x1 up to xn of natural numbers, and the functions output a corresponding n tuple, G1 of those things, G2 of those things, and so on, under which F looks exactly the way E looked on the original input. Right? So this is an n-ary reduction, and if you can do this uniformly for all n, we will say you have a finitary reduction. Okay. Just to mention, to make everybody feel like they're on a little more solid ground here, the binary reducibility here is really just plain old many one reducibility on the equivalence relations themselves as subsets of omega squared. Right? So that's something you know and love. Going up from there, it's kind of more specific to our situation, reductions on equivalence relations. I'm going to argue in a moment that going up is sort of approaching the notion of a full reducibility. There were a bunch of results about these finitary reductions and for specific arities. I'm not going to go through them right now. I'm going to put them up here and essentially make them a Zoom footnote. Meaning, I'm going to flash the slides at you. The talk is being recorded. You can download the recording and go back and stare at each slide for as long as you want afterwards and read it as a footnote. Right now, just to point out, E max is complete under ternary reducibility, but not under 4-ary reducibility. And I wouldn't have guessed that the numbers 3 and 4 in particular would come up there, but somehow they do. This is the proof that there is a ternary reduction. This is the proof that there is no 4-ary reduction. And so now they are recorded for posterity here. Okay, a little more generally, Keng-Meng and I found out that you can even fix any oracle you want, and the equivalence relation of equality of CE set, which is a little more complicated than same max, same min, right? It's a pi2 relation. For any x, this is complete among all pi2 equivalence relations, even relative to x, under the finitary computable reducibility. Okay, so you do get some useful notions out of this. Let's see, and one other surprising thing that comes out of this, I'm putting the exact same theorem up here at the top, so you can just see the correlate, the second corollary that comes from it here, is that for every Turing degree D, there are equivalence relations where okay, so second thing first, you do not have a decomputable reduction from E to F, but you actually have a computable finitary reduction. And so obviously the idea is pick D to be way high up in the hierarchy under Turing reducibility. Doesn't matter. I mean, even there's stuff that D can't do in full. There are two relations, E and F, where D cannot compute a reduction between them from E to F, but there is a computable finitary reduction. So that makes finitary reducibility seem a lot weaker in some ways, which the rest of the talk may sort of confirm. We will see. Okay. I promised, though, to talk about what happens. Well, the natural next step after 1, 2, 3, 4, 5, and the rest is to, well, starting with 2, whatever, is to ask about sort of a countable reduction. What if you give the thing countably many elements in the field? In this case, that's totally silly, right? Because the whole darn field of the equivalence relation is omega. If you can do this for countably many elements, then okay, just do it for all of omega, and you have got yourself a full reduction, right? So given that we're working with equivalence relations on omega, the notion of going to the next step, well, the next step is equivalent to full computable reducibility, okay? It's a little bit weird that right before that limit, you have this immediate predecessor step of finitary, uniform for all n, finitary reducibility. I mean, limits don't usually work that way, but in any case, this is the sense here. This is why we don't go on the next step in this context. But if you're talking about Cantor space, it might make more sense, right? In Cantor space, you can talk about reductions, countable reductions, right? So looking now at equivalence relations on Cantor space, you could talk about an omega reduction from E to F. And the idea, so you could also talk about finitary versions, of course, and possibly even it's easier to read the version down low first. For a given n, you could say, okay, what you want now is a Turing functional that accepts n reals, just spliced together, joined together this way, and outputs a real which you unsplice into n reals, and the outputs should be F equivalent if and only if the corresponding inputs were E equivalent, right? That's a finitary reduction. And then a countable one, well, same idea, except now you think of A, your single input real, as being a two-dimensional array, namely, countably many columns. So you think of a single real as being a countable set of reals, the way one often does, descriptive set theory. And you say, okay, in the input, the jth column should be equivalent to the kth column, if and only if in the output, the jth column is F equivalent to the kth column. Right? So it's the exact same notion. And now that we're working in Cantor space, it's certainly not a full reduction. So, well, what happens with this? This is something that Kang, Meng, and I proposed at the end of that paper that people should study, descriptive set theorists and stuff. Nobody did. So that sat around for maybe 4 years. And finally, I decided, okay, this has gone stale. Nobody else is going to do it. So I sat down and went through a fair amount of that myself. And so I'll tell you what came of that. I'll give you a reference in a moment, too. So no proofs here. But first of all, just to mention the standard Borel equivalence relation. Okay, so all of these come up in a lot of contexts. Well, there's a diagram down here, which is a full diagram. It gives you all the possible reductions among these things, just going up in the obvious way. Equality of reals is at the bottom. The E0 relation, which many of you will know as star equality, right? Equal up to a finite set. Okay, that's right above equality. And there's this interesting thing in Borel reducibility. It really is directly above. There is nothing in between equality and E0, and there's nothing off to the side. E0 is the second smallest Borel equivalence relation in this set under Borel reducibility. That's the Glim-Efros dichotomy, right? That's well established for some decades now. Once you get up past E0, though, things branch out and get a good deal more interesting. And so, I mean, the definitions are all here. Some natural things that you would ask, you know, to A and E1 says A and B differ on only finitely many columns. That's a sigma 2 relation if you're keeping track. So was E0, by the way, sigma 2. E2 is also a sigma 2 relation using the harmonic series to measure how bad the symmetric difference is. Okay, that one wouldn't have occurred to me, to be honest, but comes up a lot. E3, you can tell that these folks weren't thinking too much about complexity because E0, E1, and E2 are all sigma 2, and then E3 and E set and Z0 are pi 3, and so they weren't naming them with complexity in mind. In any case, E3 says on each individual column, there's a finite difference only, finite symmetric difference. E set says that if you look at, as we were saying before, if you look at a real as a countable set of reals, right? Looking at the columns in the two-dimensional array, possibly things are repeated, whatever. Okay. If you look at a real that way, then A and B name the same sets of reals, right? Not up to multiplicity, just every real that appears in A also appears in B and vice versa. So that's E set, that's pi 3 again. And Z0, which might very well have occurred to a lot of us, look at the symmetric difference and ask about its asymptotic density, right? If that's 0, then A and B are sort of pretty close to each other. Okay, so again, the standard picture is here, and it has been established that that's all that you have for Borel reducibility on these particular equivalence relations. So the question that nobody else ever took up was, what about with countable computable reducibility or with finitary computable reducibility? Well, first of all, for the countable version, everything falls into line. Okay, you lose all of these incomparabilities here. Again, I'll mention the complexity in a moment, but yeah, you can see things collapse to some extent. And then when you go to the finitary version, a little bit more collapse happens. In the finitary version, all three pi 3 things wind up equivalent to each other. And the sigma 2 things are all equivalent. And equality, which is pi 0, 1, is down there on its own. And so that's, you know, it's somehow maybe not all that surprising for us that it works out this way. But it is saying that in certain of these situations, there is a countable, computable reduction. But there's, if you look at the entire space, there's not even a Borel way to do a reduction. That seems a little strange somehow. I mean, with a countable computable reduction, you could put in, say, an element and an entire real, and then an entire sequence of reals approaching it topologically. And so you could talk about limits, and you can, you know, compute a corresponding set of reals over in the other, you know, for the other relation. You could even look at a countable dense subset of Cantor space, right? And on that, it's computable in a totally uniform way, no less, to reduce one of these reductions. But somehow when you go to the uncountable context, you know, I'll give you however many jumps you want. You still can't do it. There is no Borel reduction on no full Borel reduction, right? No Borel reduction on all of 2 to the omega. Okay, so what does that all have to do with computable structure theory? All right, well, so here's where we get to some of this recent work with Turbo and Julia. So background first, just so we know where we are here. We're going to be looking at countable structures only here. The domain will always be the natural numbers, no finite structures given. And so natural thing to do is to fix whatever signature you're in. Assume it's a countable signature, let's say, it always will be for us. Take a fixed Gödel coding with omega as sort of the constants. And so you can, for any structure A, its atomic diagram just turns into a real. And then the classes that we will be looking at in this particular talk will be the classes of particular types of structures given as these reals. So if you take the class, for instance, T-fab sub 2, that's torsion-free abelian groups, totally fabulous, right? T-fab. And what you have there is a subset of Cantor space, right? Certain elements of Cantor space that happen to represent atomic diagrams of rank 2, I was saying T-fab 2, of rank 2 torsion-free abelian groups. Okay. TD sub R will be the same sort of thing for fields of transcendence degree R over the rationals. Okay. So a few things that we should get straight here. First of all, torsion-free abelian groups, I mean, this is quite a natural class, probably familiar to a number of you, but maybe not all. You can think of them simply as additive subgroups of Q to the R, right? The rationals under just component-wise addition, except for one thing. When you say T-fab sub R, you want the subgroup to have full rank. It should contain a set of R independent elements, linearly independent. Okay. The same sort of thing applies to the fields. You can think of all those fields as subfields of the algebraic closure of a degree R extension of the rationals, right? I might as well be a purely transcendental extension, then take the algebraic closure. Once again, it's not quite all subfields of that, it's all subfields that contain R algebraically independent elements. Right? All those subfields that actually have degree R over the rationals. Okay. You should be a little bit careful about thinking about things this way too much. Because the way I'm giving them to you here, the real that you get is giving you a freestanding structure. And so if it's let's say a torsion-free abelian group, and you pick a particular element and you want to know if that element is divisible by 5, right? This is X. Is there a Y which added to itself 5 times equals X? If you're looking at a subgroup of Q to the R, there's one thing in Q to the R that could be, and you just ask, is it in Q to the R or not? But since I'm giving this to you as a freestanding structure, existence of this element, this 1/5 of X, is a sigma 1 problem, right? If you find such an element, then great, you know, yes, it exists, but there's nothing in the atomic diagram that ever tells you for certain that it doesn't exist, if in fact it doesn't. Okay. Same thing in fields, right? For roots of polynomials, if you were in the algebraic closure, you could say, oh, hey, this polynomial only has whatever 6 roots here, whatever the degree of the polynomial is, check all 6 of them. But if you're just looking at a field as a freestanding structure, you can't do that, right? You just have to wait and wait and wait until maybe someday some root of the polynomial shows up. You'll know it when you see it, but you might never see it. Okay, so these are subsets of Cantor space, so it's natural to view them as topological subspaces, of course. That puts topologies on each of these. And then you can put the equivalence relation of isomorphism. on each subspace. So now you're looking at isomorphism types of torsion-free abelian groups of this rank or of fields of this transcendence degree. Okay. A number of you probably know this quite well-known theorem of Hjort and Thomas. For torsion-free abelian groups of finite rank, they took a problem that had been around since the 1930s, since Baer started looking at it way back when, and asked just, how complicated is classification? Baer had come up with a natural classification of the rank 1 torsion-free abelian groups. Just to be clear, rank 0 is totally trivial, right? It's just the one group of a single element. So never mind that. Rank 1, Baer figured out way back when how to classify. I'll actually mention that in a moment. And rank 2 just seemed to be harder. Nobody could come up with anything good. Eventually there was a classification found, but it was pointed out that it really wasn't any better than just saying groups of rank 2 up to isomorphism. So this was a long-standing problem, and Hjort and Thomas showed that the isomorphism relation on Tfab R for any positive R lies strictly below the isomorphism relation on the next rank up, Tfab sub R plus 1. And that's even under Borel reducibility. Again, so no matter how many jumps you're allowed, you can have an oracle set for free if you want. Doesn't help. There's just no reduction of the equivalence relation of isomorphism on Tfab R plus 1 to the equivalence relation isomorphism on Tfab R. Okay. Now, I'm not prepared to tell you a proof of that. I wouldn't have time, A, and I can't do it right now, B. It goes into ergodic probability measures and stuff. It's not your grandmother's computable structure theory. So it's different, which is part of the point here. That doesn't mean that we shouldn't try to go and look at this, but it's definitely a different approach to things. Simplifying things a little bit here, there's this notion that Julia Knight and various of her group at Notre Dame developed of a Turing computable embedding of one class of computable structures into another. And so the definition actually is what I have at the bottom of this slide. It says that so first of all, it says for any, a Turing computable embedding is a Turing functional, B, which accepts as oracle the atomic diagram of any structure in the first class, K, and outputs the atomic diagram of the structure in the second class, and has the property that two structures from the first class are isomorphic if and only if the outputs on them are isomorphic. So that's exactly a reduction on equivalence relation. And the way it's defined, it's a computable reduction on equivalence relations, well, not quite on Cantor space itself, but on these subspaces of Cantor space. Okay. Now, again, computable reduction. What Hjort and Thomas says is, forget about it. There isn't even a Borel reduction, right? So this is way off. But at least in the language of Knight et al., this does imply that there is no Turing computable embedding going down from Tfab R plus 1 into Tfab R. Going up, it's quite easy, and it's written right there. The reduction is take your group and just stick an extra copy of Z onto it. And that's totally easy to compute. You have to prove that it works. It's not absolutely immediately obvious what I wrote there, that the if and only if holds. The forwards direction certainly holds. Backwards direction takes a little bit of work, but it's not hard. We can sit down and do that after this talk if you want. Okay, so that's what happens, as far as we know at the moment, with the torsion-free abelian groups, right? Here's that picture once again, strict Borel reducibility all the way up. How about countable, computable reducibility, right? You saw that question coming right after everything I was talking about for the first half hour. Countable, computable reducibility, that's the picture. TFAB 0, again, is trivial. It has a single element, so obviously it's different. But all the other TFABs are countably, computably reducible to each other. And that's really not that hard. In fact, if I get to do everything I hope to, it will come out of some stuff that I will show you later on, although it could be done a little more easily than that. Right, so the right-hand side is based on the fact there, which again, one does have to prove. You know, it doesn't jump out at you, but it works out. And again, this is kind of a surprise, just because isomorphism on TFAB1 did seem simpler in some way. Okay, well, it's simpler in the sense of full reductions, full countable reductions, even full Borel reduction. But still, you can take countably many elements of TFAB2 and produce for each of them an element of TFAB1 and preserve the isomorphism relations on those things perfectly. And it doesn't even matter which countably many things in TFAB2 you're given. It's the same reduction, no matter which countable set you get. So let me tell you just a little bit about the isomorphism relations. The one that seems pretty simple on TFAB1, here's what you do. You've got a TFAB1 group. I have another one. You pick a non-zero element in yours, which already by itself constitutes a basis because it's rank 1. I pick a non-zero element in mine. And then we go through and start filling in the elements of this set I sub G. That's not decidable from what we've got. It's computably enumerable, right? You say, okay, for each prime power, p to the n, given your element in your group, is there a p to the nth, not a root, does your element divide, does p to the n divide your element in the group? And does p to the n divide my element in my group? Now, depending on which basis elements we pick, we might get different answers sometimes. But if the groups are isomorphic, we will only get finitely many different answers. Basically, whatever the isomorphism is, it maps your basis element to a rational multiple of mine. And so we'll be off by whatever the numerator and denominator were. And that's about it. So this kind of comes back to asking whether two reals are E0 are star equal, right? Whether E0 holds of them. The only thing is the reals in question are sets that we enumerate from the atomic diagram rather than having them pull out. So this turns out to be a sigma 3 isomorphism. This relation turns out to be sigma 3. As you go further up, hang on. No, there. Okay. As you go further up, r greater than 1. Now the issue is you can't just say pick one non-zero element. You have to say pick a basis. And if you just pick two elements at random, it's not obvious whether they're a basis or not. They might be scalar multiples of each other, and that's not in general decidable in the atomic diagram. So that's why it seems harder. Well, it is harder, but on the other hand, it turns out it's still sigma 3, right? I mean, so the full statement is that there exists a basis in your group and a basis in my group, such that the linear combinations of your basis that appear in your group are exactly the same ones as the linear combinations that appear over my basis in my group, right? If there exists such a basis in each of these, then the groups are isomorphic, and conversely. Okay, so it seems a little bit harder because of the stuff with picking the bases, but it's essentially just tacking an extra existential quantifier onto a sigma 3 statement in some way. So it's still sigma 3. Okay, so it's plausible here that there is a computable countable reduction, and indeed there is. I told you that already. Yeah, so that's the situation for quotient-free abelian groups. Let's talk fields for a moment. Fields are in general very similar. Let me just get out of the way, first of all, the r equals 0 case. R equals 0 for fields is not trivial, right? There are lots of fields of transcendence degree 0 over the rational. Rationals themselves, sure, but any other any other subfield of the algebraic closure of the rational would do it. Okay. And in that situation, isomorphism is pi2 because you don't have to choose a transcendence basis there. You can just say, okay, essentially, which polynomials have roots in which field? Is it true that every polynomial over the integers, one variable, it has a root in my field, has a root in yours, and vice versa? That's a pi2 statement, and it's equivalent to isomorphism. If you go up to positive transcendence degree, then once again, you have to pick a basis first. And so that adds an existential quantifier out front. But beyond that, it works pretty much the same way. Two of those fields are isomorphic if and only if yours has a transcendence basis and mine has a transcendence basis such that exactly the same integer polynomials in one variable over those transcendence bases get realized. Okay, so it feels very much like the situation for torsion-free abelian group. Right? I mean, finding a basis and then sort of saying which holes get filled in. Okay. So what happens? First of all, this is something we still don't know for sure. Can you go upward in field? Okay, you know what I mean. In the picture for torsion-free abelian groups, which I'll bring back in a moment, you did have reductions going up, right? Tfab1 computably reduces Tfab2 and then to Tfab3 and so on going up. In fields, we believe we can do that. It's certainly true when R equals 0. It's very simple. In fact, you just take a purely transcendental extension of each field. It's sort of the right analogy to adding a copy of Z in torsion-free abelian groups. Okay. And that does work because the fields E and F are within E of T and F of T. E and F are exactly the subfields consisting of the algebraic element. And so any isomorphism between E of T and F of T would have to map E onto F. And therefore E and F would be isomorphic. Okay, so that's one direction and the other one is trivial. For R greater than 0, the same process should work, but we're not there yet. I can explain to anybody who's interested what the holdups are. But fields do seem to be a bit more complicated than torsion-free abelian groups this way. Okay. There is a separate attempt which involves trying to adjoin the entire algebraic closure of a new transcendental. And the problem is that sort of obliterates the algebraic parts in the original field. You wind up taking the algebraic closures of both of them. So that, in a way, that reflects the fact that whereas Tfab0 was totally trivial, TD0 is not. It's got a lot of different possibilities. Continuum many. Okay, so going upwards, therefore, all we can actually fill in for certain right now is the thing all the way on the right. And it is strictly less because isomorphism in TD0 is a pi2 property and isomorphism in TD1 is a sigma 3 property. Okay. So I said current picture. I'm about to fill in a little bit more. Then it will be the current picture. Obvious question, what about right to left and left to right? Okay. And we have proven that you can go from left to right by a computable reduction at each individual level. Okay. So that's nice. I'm going, I feel like I'm, whatever. Yeah. Okay. I'm going to tell you about that just a second. Yeah, so the idea of this reduction is pretty simple. Again, so the situation here is you're given a torsion-free abelian group, and you're supposed to compute a field of the same transcendence degree as the rank of the group. And the idea is that, well, addition you don't have to preserve addition, but it's helpful to. Addition in the group should sort of go to multiplication in the field in the following sense. If you have a basis for the group consisting of R elements in the group, assign to each of them one of these new basis elements, big X1 up to big XR, which are going to be a transcendence basis for the field that we build. There's the right number of them. And then every element of the group is uniquely a Q-linear combination of that one basis. Whatever the Q-linear combination is, you add to the field a monomial with the corresponding exponent. So I didn't do an example here. I just said, if you have an element A1 up to AR, right, group element written in terms of this particular basis, then put into the field the element X1 to the A1 up to XR to the AR, monomial that way. Okay, now that's not enough right there, so details. First of all, you've got to guess at a basis for the group. But the good news is, if you're wrong, you can actually cover your tracks totally easily. And you'll only be wrong finitely many times. Sooner or later, you're going to hit on an actual basis. You may not know it, but you'll never be wrong again. Okay. So second of all, we said, okay, just take, x3 to the 7/2 power or something like that. Well, there are two such elements in the field. If it were x3 to the 7/5 power, there might be 5 such elements. Okay, well, so let's work in a fixed real closed field with the right number of transcendental, of independent elements. And then when you want to take a square root, just always take a positive one. And that removes all possible ambiguity there. You do have to close under the field operations, of course. I mean, monomials by themselves here do not form a field. You need to take Q-linear combinations of them and then quotients of those things. And that makes the proof a bit more complicated. I mean, the easy part here is that, of course, if E is isomorphic to H, then you do get 2 isomorphic fields here. You might have chosen different bases, but there's an isomorphism between the groups, and that converts very quickly to an isomorphism between the fields. The problem is to show that if the fields turned out to be isomorphic, does that actually mean that the groups work? That takes work. And again, I can sit down and show you, we have a proof of it, but that's not trivial, and that takes a moderate amount of work. So here's this picture. I mean, I already filled in those left to right arrows. One thing this means, now remember, there are no Borel reductions going down the left side. And that means that, among other things, you can't try to cheat, right? You can't go over to the right, down on the right, and back to the left in a Borel way. Okay, now we know that you can go over to the right, computably, no less. So one of the other two has to fail. Either there's no downward reduction on the right, or there are and again, either there are no Borel reductions downward on the right, or there are no Borel reductions from right to left. Okay, or possibly some combination of those two. That would be totally weird, but theoretically possible. Our conjecture is that both fail. That's still open. I mean, don't have a proof of that. So the conjecture is mainly just because we've tried awfully hard and haven't found anything yet, which is not all that good evidence, but okay, anyway. But I want to fill in a last fact here. Going back to the theme of the talk, for every R, there is a countable computable reduction from the TDR class, any one of those on the right, down to TFAB 1. Again, TFAB 0 is sort of different. It's trivial, and TD 0 is also different in its own way. So ignore the two bottom ones. But everything else above that is countably computably equivalent to each other. Okay. And let's see, all of them reduce to TFAB 1. I guess TFAB 0 does. TD 0, yeah, you can go up and over. Yes. Okay. Yeah. Okay. Yes. So yeah. So for every R. Yeah. Okay. Right. What I will say about this, I was wondering if I should drag you through it, and I think the answer is I don't have time. This is very much a traditional computable structure theory proof. I mean, this involves guessing at a basis and then setting up a game with chips where an isomorphism corresponds to getting infinitely many chips, and then looking at finitely many, assigning primes to each of various cases and having them sort of be off by one in the group that you build at each step. And if you wind up doing it infinitely often, then of course you come out equivalent. But if not, then they actually are off by one. And so if there are more than finitely many things that go wrong, then the groups that you build are not isomorphic. On the other hand, if there actually is an isomorphism, then only finitely many things go wrong, and the groups that you build are isomorphic. Okay, that was a total hand-waving version. But the point isn't to drag you through it. The point is to get you to believe this is your grandmother's computable model theory. Okay, I mean, it's fairly advanced, but it's the same sort of thing that we've been doing all along. Okay, this is just the rest of that argument. So again, zoom footnote. Okay, further point here. The reduction from so the left to right reduction from TFAB R to TDR actually extends to, it's a computable reduction, and it extends to a computable functor, for those who know what that is. So if you have an isomorphism given to you between two, obviously isomorphic, copies of a group in TFAB R, then from that isomorphism and those two copies, you can compute corresponding isomorphism between the two fields that are spit out by this reduction. And it is a functor, it's functorial, it respects composition of isomorphisms and all of that, which is a nice fact. Leads to a question going back to other Borel reductions. Is there anything similar there? Okay, so let's see. Thinking of this notion of computable functor. Now, okay, so isomorphisms attach naturally to the property of being isomorphic. For the other Borel equivalence relations that we discussed, I mean, well, they aren't sigma 1, 1 hard, but neither was isomorphism on these fields and these groups. There are situations where you can think of a sort of a witness to one of those equivalence relations. So for instance, the Z0 relation, which says that the symmetric difference has asymptotic density 0, you could say a witness would be a function that tells you when you've gotten to the point that the density of a triangle B will never again be greater than 1 over D. But it goes to 0 as n goes to infinity here. So there's some point past which it's always less than 1 over D. A function that witnesses that would, I mean, it's not like an isomorphism exactly, but in some sense, it's the thing that makes this, makes the limit be 0, makes the equivalence relation hold of these two elements. I wonder if there's any sort of analog of saying, okay, I could take, something like that for Z0 and do a reduction of Z0 to some other relation and, do something kind of functorial with those witnesses. Pie in the sky stuff right now, but it's worth a thought, okay? And let's see, wrapping up, basically, our feeling here is that, yeah, I mean, I told you that the proof going from left to right was very much traditional computable structure theory. The other stuff is just different order of magnitude somehow. It seems like it's going to need some different techniques. Again, you're talking about full Borel reductions there, and that's just a whole lot harder. You can sort of work in between, saying, what could I do if I had a few jumps? What level of Borel map might or might not exist? I mentioned already the question about what sort of functoriality might be possible in other Borel reducibilities or computable reducibilities. And then again, the strange thing that, these countable computable reducibilities give you this very effective way to take even a dense subset of Cantor space and do a reduction on the whole darn set. But at the same time, it can be impossible to do even a Borel reduction on the full set all at once. Okay, that's something that we ought to study. You know, that's a spot where these two areas of logic ought to meet and discuss. Okay, and so I will leave it at that. Thank you all for your attention.
Thank you very much, Russell. Does anybody have any question?
Thanks, Russell. Yeah. So am I right to say that a lot of the equivalence relations you're looking at they're not countable, as in they have uncountable classes, right?
Okay, yeah. So in the computable structure theory, well, let's
Russell,
see.
would you mind repeating the question for the Zoom?
Okay, so thank you. The question is about whether these are countable equivalence relations, where the definition of that is that the individual equivalence classes are countable. And that plays into a number of the results in the Borel theory, definitely. Let's see. Don't want to say all of those right off the bat, but certainly most of those are countable equivalence relations. I'm just getting back to the list of them here. Yeah. Yeah, I mean, finite difference, differing on only finitely many columns, that can be uncountable. I mean, the first column can be anything at all.
Right.
No, actually, most of these are uncountable here, I think. Every n having finite symmetric difference, every column having finite symmetric difference. No, that's still infinitely many columns where you can, yeah, that's uncountable. Okay, so most of these are uncountable. And
Great.
yeah, when you, yeah, so.
Yeah, okay, so therefore my second question would actually make sense, which is that, how about the notion of countable reduction, where instead of countably many points, how about we have countably many classes or something? Do you think that's interesting? Or yeah.
Okay, so the second question here is, what if you have an equivalence relation on Cantor space, but with only countably many equivalence classes, right? No, okay, hang on.
What if you have a notion of reduction instead of this countable reduction that you define, which sort of doesn't work on whole space, but only works on countably many points? Now, how about we consider a variation where it works on countably many classes?
Okay, so you can pick out countably many classes, which might have uncountably many things in them, and it should work on anything at all from those classes.
Yeah.
I
guess he said it.
It might still be possible. I mean, so the first thing, I mean, you can't really give a Turing functional more than countably many reals at a time, right? How would you do it? So I think if I'm understanding the question right, that's the first hurdle here, is just how would you describe a countable reduction in this form? If you could, then it might work. Again, it might come down to something like saying, okay, never mind exactly which things I'm given, but give me, for instance, for the asymptotic density 0, give me a function which says how soon the asymptotic density gets down to 1/2 to 1/3 to 1/4, and so on. So if you sort of clumped things together, I mean, a number of, I guess there would only be countably many reals with the same function, right? Because, well, oh, even that, maybe not. Maybe, well, okay, it's something to think about. I'm kind of floundering around trying anything here. You can see, I don't know right now. Worth a try. Yeah.
So I think I saw one more question.
Over there. Yeah.
which for reasons of time will be the last question, but any other questions you can ask Russell in person.
Thanks. So you've mentioned that the sort of countable version looks like it should be stronger than it is for the examples that you've looked at. Have you tried to identify, say, some properties of equivalence relations such that for those relations having a countable reduction can actually be lifted to giving you the full computable version?
Yeah, I wouldn't say there's yeah, the question, let me see if I can say this question properly, is whether we've considered which equivalence relations may have the property that a countable computable reduction would automatically guarantee, which ones may have some sort of property under which a countable computable reduction would automatically guarantee a full countable even, or at least Borel reduction. I don't think there's anything, I mean, again, I think that's mostly a no. I mean, I've sat and wondered sometimes just about the topology of this. I mean, my very first gut reaction was totally wrong. It was, oh, hey, you know, if you can do things on a countable set, that's sort of a local version of a full reduction, isn't it? And of course, it isn't, because I mean, even a neighborhood of a point is going to be uncountable. So at least in a strict sense of local, you know, you don't succeed on a neighborhood, you just succeed on kind of a countable set. I still wonder if it has something to do with, you know, sequential arguments, because you can talk about a countable sequence and its limit. You know, you might have to put the limit at the beginning instead of at the end, which is aesthetically unpleasing, but, you know, it would still work. So, I mean, this is something I was sort of wondering if any of the topologists here have come across, just a notion of you know, what is the analog of being able to do these things on, being able to do this sort of effective continuous process on countable sets, but not on the whole space. So, so I've turned that into a question for you. This is a very good tactic.
All right, so the further discussion of any of this will continue in the break, but don't leave yet. Let's thank Russell one more time. Thank you, Russell. And we have a small schedule.